Hello, good afternoon. Well, I'm going to speak about the relation between genotype and phenotype. The map between them, it's not one-to-one. So there are many genotypes that are compatible with the same phenotype. Well, what is a genotype? For us, it's going to be the DNA, and our phenotype is going to be the feature that you can see. And it's not one-to-one. For example, many people have the same color of eyes, but all of them have different DNA. So we are going to try to relate this relation between genotypes and phenotypes. Our aims is to characterize the geometrical and topological properties of this space using robustness and evolvability. We would like to study dynamical evolution and also how features depends on the properties of the corresponding gene regulatory networks, and analyze the effect in this application in dynamics with competitive populations. What is our model? The gene regulatory network is modeled as a graph where nodes correspond to genes and interactions correspond to edge. Each edge has associated a weight, +1, -1, or 0. +1 means that one gene promotes the other one, and -1 means that one gene inhibits the other one, and 0 that doesn't exist any edge. This gene regulatory network is with these weights, it's going to be our genotype. If we change only one of these weights, it's going to be called, there is a mutation between one genotype to another one. So we also have an initial state. Each gene has a state +1, -1, activate or inactivate. And the final, we put a dynamics with this initial state, and the final state is going to be our phenotype. How to represent this in this space, genotype-phenotype space, with a pseudo-bipartite graph, where nodes are going to be genotypes. We can see here genotypes in different colors than gray, and phenotypes, there are going to be nodes in gray. There are two kinds of edges between them, genotype edges, that corresponds at this kind of edges is when, thank you, we only differ one mutation between these genotypes, and genotype-phenotype edges, each genotype has associated a phenotype as a final state. And we would like to study properties of this kind of networks. For example, robustness, that is a measure to resilience to mutations. We are going to study this using clustering coefficient, for example. And also we are interested in evolvability or innovation, that is the ability for adaptation. We are going to study this using the diameter of the graph, shortest path, for example. Well, some results and some conclusions. We have seen that robustness and evolvability evolve together. So as time happens, clustering grounds. Also, we have seen that genetic regulatory network parameters affect percolations. And also, we have seen that a Giant component appears as clustering grows. We can see as clustering grows, so a Giant component appears. Some conclusions and future work is, well, we have seen that robustness increases with time. There is a strong relation between clustering and degree. And we would like to study how rewiring the gene regulatory network affect to the robustness and evolvability, analyze this application with different kinds of populations, and model viability conditions from the point of view of the dynamics of the gene regulatory networks. And this is all. Thank you very much, Noel, and to my supervisor.